Good morning, ladies and gentlemen. Today, we are going to be working on molar volume. Okay, we've spent the last couple of days, we worked with Avogadro's number, we worked with molar mass, and now, again, we're going to work with molar volume today. So let's take a look at what about. So, very quickly, we started off last class, or the last classes, talking about molar mass. What is molar mass? Molar mass is 1 mole, right, of stuff. And it's the mass of that 1 mole. Mass is given in the unit grams. So that's right here. So it's the number of grams of stuff, right? That's 1 mole of the stuff. And remember, that's that number 602 hexillion. So molar mass, we get it from the periodic table, okay? So hydrogen had a molar mass of 1.01. Fluorine has a molar mass, no, let's say oxygen has a molar mass of 16. H2O, which is 2 hydrogens and 1 oxygen, has a molar mass of 18.02 grams per mole. Now, the units grams per mole is what makes molar mass molar mass. It's all about the units. So you can see the units for molar mass are grams per mole of stuff. Then we worked with Avogadro's number. Avogadro's number, it basically says that 1 mole equals 6.02 times 10 to the 23. So if you have 6.02 times 10 to the 23 of something, you have 1 mole. And so this number allowed us to find out how many individual atoms or molecules we'd be working with. For example, if we have 12 grams or 12.01 grams of carbon, and we know that 12.01 grams of carbon equals 1 mole of carbon, then we know how many atoms of carbon we have, because 1 mole is 6.02 times 10 to the 23rd. So if you have 1 mole of carbon by mass, then you must have that many molecules or that many atoms. And then if we said we have 6 grams of carbon, or 6.005, which is exactly half of this number, so we have 6 grams of carbon, right? It's not 6 grams per carbon per mole. This would actually be half of a mole, which means we'd have half that number of particles. But we worked all these things out last class. So today, we're going to be talking about molar volume and then how to convert molar volume. All right, so let's take a look at what we have. Number one, gases, ladies and gentlemen, can take up all sorts of different shapes. All right, and you probably know this. You know that if you have something that's cold and you put it, or you have something and you put it in the refrigerator and it's a gas, like a balloon, that balloon will shrink down in size. And if you don't know that, you'll be learning that this year. So cold things take up less space. Space is another word for volume. Cold things take up less space, and hotter gases take up more space. With that said, if I give you 5 gas particles, you can't tell me how much space those 5 gas particles are going to take up, because a cold gas might take up that much space, and a hot gas, because hot gases take up more space, those same 5 molecules might take up this much space. So temperature will determine the amount of volume or space. We also have to deal with pressure. Pressure, since we're not in the classroom, I'm going to have to give you some videos on it, but that's not the point of this class. High pressure is when you would take your hands, where you take something and you squeeze in and you put high pressure on it. Low pressure is when you wouldn't have very much pressure and you'd actually just kind of hold something, where's the video? Hold something in like this. So this would be low pressure, and this would be high pressure forcing it in. And we can see that with these molecules. If in here, right here, we have 100 molecules in there, okay? 100 molecules of gas. and it takes up this much volume, okay? If I push in this piston and I move the piston all the way over here, and I just force all that air in, or whatever, right? The air that's already in there. And now there's my piston wall. I still have 100 molecules in there, but these 100 molecules now are in a smaller amount of space. So the amount of pressure that's on a system will determine how closely packed together these gas particles are. All right, so my whole purpose of that is that gases are affected by temperature and by pressure. And we have to take that into account, which we'll do when we're doing these conversions. So since gases have different volumes, different amounts of space at different temperatures and at different pressures, scientists need a way to work together. And the way they do that is they came up with something called STP. STP. The S stands for standard, the T stands for temperature, and the P stands for pressure. So standard means everyone in the world is going to use this same system, and the standard is going to be the temperature and pressure, because both temperature and pressure affect gases. So we don't need to know this information, but I'm going to share it with you. The standard temperature is 0 degrees Celsius. 0 degrees Celsius is the temperature that water freezes. That's also known as 273 Kelvin. Since we live in America, I believe we freeze at 32 degrees Fahrenheit. I always forget because I don't really use Fahrenheit. All right? I use Celsius. So that's the standard temperature. The standard pressure, ladies and gentlemen, is something called 1 atmospheric pressure. So 1 atmospheric pressure is the amount of pressure that's pushing down on 1 atmosphere. Another unit is 760 millimeters of mercury. One that you might be familiar with if you ride your bicycle is PSI. So the PSI that you're familiar with is pounds per square inch, and that's something that we work with when we're filling up our bicycle tires. And for us, 14.7 PSI equals 1 atmosphere. But again, we don't need to know this for another couple of months. All right, I'm just letting you know that there are specific numbers that go along with STP, but you don't need to know what they are right now. So what is STP? Well, again, that's standard temperature pressure. Now, at that standard temperature and pressure, ladies and gentlemen, 1 mole of gas. So for every 1 mole of gas, you will have 22.4 liters. How much is 22.4 liters? It's about this much. So if you've seen those like little 5-gallon water containers, it's about 22.4 liters. Or kind of a big beach ball. A big beach ball is about 22.4 liters. I have some of these in my classroom, but size is relative as we're doing a video. So what is our ratio? Well, the ratio or the conversion factor that we're going to use to solve for volume is 22.4 liters for every 1 mole. And that would be 22.4 liters of a gas. This only works with gases. So 22.4 liters of helium, okay, takes up this much space. 1 mole of nitrogen gas will be 22.4 liters at STP. So all gases are going to have the same volume at STP. And it says it here. This idea is true for all gases. 1 mole of a really big gas like carbon dioxide, a big gas, carbon dioxide, oof, there's carbon dioxide, is going to take up the same amount of space as this little tiny hydrogen gas particle. So in here, doesn't matter, at STP, 1 mole equals 22.4 liters. And we'll be using these conversion factors to solve. Now, we're going to start solving problems, which I'm going to solve relatively quickly to save you time, because we've already started conversion factors, and you should be getting pretty good. And if you're not, you need to stop me and say, hey, Mr. P, I need you to work with me. Take me into a breakout room. Would you please work with me one-on-one? We have to get this down. A couple of you have been changing my example. So I'll put an example on the page and you guys will actually rewrite my example to get a wrong answer, which confuses me, but I'm gonna ask you not to rewrite my examples. They're there for you to follow along. So we're gonna do this the same way we've done all of them. First thing we're gonna do, let's solve this equation. Now we're gonna be using molar volume to do this. What's molar volume? This is molar volume right here. All right, read the question. You have 145 liters of nitrogen gas. Okay, we've got 145 liters. And how many moles do we have? That's what we're looking for. Wait, at STP, what is that? That means we can use this number because these numbers are at ST, and P. Probably looks like a plus sign. I don't know why we're not working here. Oh, that's why. STP. All right, so here we go. We have 145 liters, so many moles. First thing we want to do, always write down what we're solving for. So we're looking for moles of N2. What are we given or asked to convert from and into moles? We're asked to convert from 145.00 liters of nitrogen gas. So at this juncture, we're going to come down and I'm going to ask you straight away, which one of these conversion factors are we going to use? Do you think to convert liters of a gas into moles, we're going to use this top conversion factor, A, or do you think we're going to use conversion factor B? That's right. We're going to use conversion factor B. Why? So that we can cancel out the liters. So we have the liters of nitrogen gas, right? There's liters of nitrogen gas. And up here, we're going to have moles. Whoops. We're going to have moles of nitrogen gas. But what numbers go with them? Well, it's always going to be per mole. So per 1 mole, and we're going to have 22.4 liters of nitrogen gas. So the problem's over. Why? Well, because the liters of nitrogen cancels with liters of nitrogen, we just have to solve mathematically. Again, some of you were struggling on solving. Remember, as we multiply, as we go across, we multiply, and the numbers on the bottom, we're going to divide. So to work this out, this is going to be 145 times 1 divided by 22.4 equals our answer. So I just broke out my Desmos calculator. All right, you have access to this on my home screen. So I'm going to type in 145 times 1, because we're multiplying it times 1. We could put parentheses around this as well if you want to make it look exactly like the problem. And then you can push divided by, and look, it puts it there, 22.4. Very little thinking we even have to do. And if you, whoopsies, and if you take a look, this problem looks exactly like this one, 145 times 1 over 22.4, and that's our answer, 6.472. Now, I've also, as a teacher, I don't like caving, but I'm going to cave on this one. We're going to go just to 2 decimal places, okay? Kids are really struggling trying to save those 3 decimal places. So now, if you save 3, that's fine, but you have to save a minimum of 2. So this answer will include this much right there, okay? And then so we're going to have 6.47. Then we're going to look and see if this 3 rounds that 7. Does the 3 round the 7? No, it does not, which means our answer is just going to be 6.47. 6.47 moles. Does that number make sense? Some of you have numbers written down that don't make sense at all. Does it make sense? Well, sure. If 1 mole is 22, or about 20, 20 times 6 is about 120. So yeah, that number makes sense because well, I'm going to work with that. I'm going to work with you on that stuff, seeing if numbers make sense. All right, so let's move on. Let's take a look at question number 2. Question number 2 is the only other version that I can ask. All right. So first thing we do is we read the question. We have 12 moles of chlorine gas. How many liters of chlorine gas will we have at STP? What is the first thing I'm going to write down, ladies and gentlemen? That's right. I always write down what I'm looking for, what I'm trying to solve. What am I trying to solve? I'm trying to solve for liters of chlorine. All right, liters of chlorine gas. What am I starting with, or what am I asked to convert? That's right, 12.5 moles of chlorine. So at this juncture, we're trying to get from moles, it's a gas, so we're trying to get from moles to liters. Do we know a conversion factor? What is the name of a conversion factor that allows us to convert from moles to liters? That's right, kids. The name of the conversion factor is molar volume. Okay, because it allows us to convert moles to volume liters, right? Moles to liters. So here's our example right over here. Are we, ladies and gentlemen, going to use example A, conversion factor A, or conversion factor B to solve this problem? That's right. We're going to use conversion factor A, ladies and gentlemen, because we want to cancel out the word moles. So I'll put moles at the bottom. 1 mole, and it's going to be of chlorine gas. I just won't write the word gas. And then at the top, it's going to be the other half of this conversion factor, which is 22.4 liters of chlorine gas. Whoopsie daisy. Capital C there, of chlorine gas. And we're pretty much done. Did I do that right? Did I just give the same example twice? Liters to moles, moles to liters. Oh, good. All right, so, yeah, good one. All right, so, ladies and gentlemen, what do we need to do? We need to multiply all the numbers on the top, divide the numbers on the bottom. So let's clear out our calculator. Let's put in 12.5 times, if you want, I'll put parentheses around that. Okay, 12.5 times 22.4 divided by 1. Click out, close the parentheses, and there's our answer, right? Because 22.4 divided by 1 is still just 22.4, all right? And we're just multiplying that 12.5, and our answer is going to be 280 liters. All right, so ladies and gentlemen, if you're struggling with this, you got to let me know. Again, there were a couple of students, and I don't know why, they were coming in here just writing. There would be something like this, would just be like 6 liters, and over here would be like 14 grams. And I'm like, this is my example. Please don't mess with the example. If you're ever like, I don't understand what to do, then look at the example, because yours is going to be set up exactly like that. You just have to find the right one. It's not rocket science. It's just following patterns. So see if you can follow the pattern. Ladies and gentlemen, that's it for today. Hopefully you're doing well on understanding how to convert. This is just the beginning of converting in chemistry. We've now had 3 different conversions that we've been practicing. And I really hope that you're starting to go, oh man, the top cancels with the bottom and the top just goes across. We just have to find the right conversion factor. Exactly, ladies and gentlemen. So have a good day, and I will be here if you need me.